Welcome to this video on heap sort. Now, before I get into heap sort, there are a few prerequisites that we need to keep in mind. So this is one of them. First, you need to know the array representation of a binary tree. So what I would request you to do is pause the video and note it down. So I hope you have noted it down. Now what I'll do is I'll just quickly explain these points here. Okay. So here you can see that first let's look at the assumption. The assumption is that the array indexing starts from 0 in most programming languages. In fact, I am recording this series of videos for data structures with C programming, and we know that arrays in C start from 0. So the rules that I have written is that the rules that you see here, the three rules that I've written here, are based on the assumption that array indexing starts from 0, as it is the case in C programming, and also the root is always at the first index. Okay, so my root node of the tree will always be at the first index, that is at index 0. Okay, now what I'll do is I'll just explain these rules quickly. So if you have a node which is, let's say, at index I, what you will do, you will take your two-dimensional representation of a binary tree and store it in an array. Now if you take up a particular node which is, let's say, at index I, then if you want to find the left child, here LC stands for left child, if you want to find the index of the left child of the node which is currently at index I, then you will have to use this relation, you will have to use this formula. And if you want to find the right child of a node which is present at index I, you would have to use this formula. And what if you want to find the parent? So if you want to find the parent, then you will have to apply this formula. What does this stand for? This is the, if you remember, this is the floor function. This is the floor function. So I'll just take a couple of examples. So if I have to find the floor of 3.6, what would be the floor of 3.6? Floor of 3.6 is the integer which is less than 3.6 but which is closest to 3.6. So floor of 3.6 is the integer which is less than 3.6 and which is closest to 3.6. So the integer which is less than 3.6 as well as closest to it is 3. Okay, sorry about that. So here the floor value of 3.6 would give me 3. Similarly, if I take let's say the floor value of minus 3.6. So what if I try to find the floor value of minus 3.6, then what would I get? Again, this would be like in this case the integer which is closest to 3.6 and which is less than minus 3.6. Here you have minus 3.6, right? So here floor of minus 3.6 will be the integer which is closest to minus 3.6 and which is less than minus 3.6. So which is the integer which is less than minus 3.6 and which is closest to it? It's minus 4. So here the answer would be minus 4. Okay, so here the answer would be minus 4. And so I hope you have understood what the floor function does. So if you have to find the index of a node, if you have to find the index of a node, and if you have to find the parent, rather, let me put it this way, if you want to find the parent of a node whose index is I, then you would apply this function provided your I is an odd value. And if you have to find the parent index of a node which is at index I, then you would have to apply this formula if I is even. Okay, so this is what the formula is all about. Now what I would do is I'll take up a few examples and show how these formulas actually work. Now let's look at these two examples. Okay, so here I have a binary tree rooted at A. Here also I have a binary tree which is rooted at A. That means the root node is A. Here also the root node is A. Now if you remember from the formulas that I just showed you, the root node always goes into the first index. And which is the first index here? The first index is 0. So my root node which is A goes into the first index. Right? Up to this point it's clear. Now what do I have to do? I have to fill up this array to represent this entire tree. Now where would the left child of A go? The left child, if you remember, the formula for finding the index of left child is 2 into I plus 1, and the formula for finding the index of the right child is 2 into I plus 2. Okay, now I want to find, I know the index of the root, the first index. Now I want to find the index of the left child. The index of the left child would be, whose left child am I talking about? I am talking about the left child of A. And what is the index of A? The index of A is 0. So what would be the value of I in this case? The value of I in this case is 0. So 2 into 0 is 0 plus 1 is 1. That means the left child of A, which is B, will go into index 1. Now let's try to find the index of the right child of A. So this becomes index 1. This goes at index 1. What about the right child of A? P. Where will this go? It will go at 2 into I. What is the value of I? The value of I is 0. So 2 into 0 is 0. 0 plus 2 is 2. So the right child of A will go at index 2. So P goes at index 2. You'll observe one thing very closely in a short while. After I fill up this entire array, you'll observe one thing and then you would come to another conclusion. Okay, now let's see. I want to find the index of C. What is C? C is the left child of B. How do I find the index of C? I'll apply this formula. So left child of B. I want to find the index of the left child of B. What is the index of B? The index of B is 1. So 2 into 1 is 2. 2 plus 1 is 3. So C will go at index 3. Similarly, I want to find the index of the right child of B. The right child of B is D. So what would be its index? Its index would be 2 into I. What is I? I here refers to node B. And what is the index of node B? 1. So 2 into 1 is 2. 2 plus 2 is 4. So D will go into index 4. Next, I want to find the location of G. So how do I find the location of G? Now in order to find the location of G, I have to see who its parent is. The parent of G is C. What is the index of C? 3. So what would be the index of G? G is to the left of C. So I would apply this formula to find the left child. So here I will be the index of C because I want to find the left child of C. So the index of C here is 3. And so its left child will be at index 2 into 3, 6. 6 plus 1 is 7. So G will go at index 7. Now let's try to find the index of E. See, I want to find the index of E. What is E? E is the left child of P. What is the index of P? The index of P is 2. So I'll apply 2 here in place of I. So 2 into 2 is 4. 4 plus 1 is 5. So E, which is the left child of P, will go at index 5. Similarly, the right child of P is F. How do I find its index? I apply this formula. What is I? I is the index of the node whose right child I want to find. So whose right child do I want to find? I want to find the right child of P. What is the index of P? 2. So I'll place 2 here. So 2 into 2 is 4. 4 plus 2 is 6. So the right child of P, which is F, will go at index 6. Now observe one thing. Here, if I decide to, so here I applied the formula and I filled up this array. Now what if I tell you this, that if my binary tree, okay, just give me a moment. Let me just erase these marks that I made here, these annotations, so that you can visualize what I'm trying to say even more clearly. Now see, this is the tree that I have represented in this array. Now, what I would say is, if you have such a tree, what is this kind of a tree called? This kind of a tree is called a complete binary tree. It's called a complete binary tree. Okay, so how would you define a complete binary tree? You would define a complete binary tree to be a binary tree which contains maximum number of nodes at all levels except the last. So this is your level 0, this is your level 1, this is your level 2, and this is your level 3. So which is the last level in this tree? The last level is level 3. Now I'll not consider the last level. I'll consider all levels before the last level. So all levels before the last level are 0, 1 and 2. So up to this point, see, my levels are full. That means I cannot have more than one node at level 0. I cannot have more than 2 nodes at level 1. I cannot have more than 4 nodes at level 2. So all levels preceding the last level contain maximum number of nodes. And what about the last level? The last level, if it contains nodes, it should be filled up from left to right. So see, here G is present at the leftmost point. See, how many links are possible at the last level? You can have here, you can have 2 more here, 2 more and 2 more. So many links are possible, 8 links are possible. Where should I start filling up? I should always start filling up from the left end. That means if I have to, like here I have G, then I'll have to start from the leftmost point. Then let's say I want to insert another node. Let's say I want to insert H. Then I have to insert it here in order for this complete binary tree property to hold true. If I want the complete binary tree property to be applicable on this tree, then I need to fill it up from left to right. That means here I've taken G. Next I would use this position to insert another node. Next I should use this position. Next this position. Let's say if I jump, instead of, let's say I want to insert another node. At this scenario, I want to insert another node in this tree. And I want the complete binary tree property to be followed. If I skip this part, if I skip this link, and if I decided to insert a new node here, then it no longer remains a complete binary tree. It no longer remains a complete binary tree. So remember, if you are filling up nodes at the last level, you must always do it from left to right without skipping any links. So if I skip a link here, now this tree that you see here is not a complete binary tree. But up to this point, it's a complete binary tree. And the tree which I actually had here with G at the last level is of course a complete binary tree. So you can write down a complete binary tree is a binary tree which contains maximum number of nodes at all levels except possibly the last, and the last level nodes are filled up from left to right without skipping any links. So you can pause the video and note down the definition which I just mentioned. So this is how you would fill up an array for a binary tree. Now one thing you may observe is there are no gaps in this array. That means I haven't skipped any index position. All indices have been filled up continuously. This is made possible because of the fact that this tree is a complete binary tree. Remember, complete binary tree has this property that it does not waste any array space. If you're trying to represent a complete binary tree through an array, there will be no wastage of space. That's why we use an array to represent a complete binary tree. Always, we will use an array to represent a complete binary tree. Now, if you observe, this is not a complete binary tree. Why? Because, okay, how many levels are here? This is level 0, this is level 1, and this is level 2. So, preceding the last level, level 0 contains maximum number of nodes. Level 1 also contains maximum number of nodes. But coming to the last level, I have skipped these 2 links. I should always start filling up my last level from the leftmost end if I want the complete binary tree property to hold true. But I have skipped these 2 links and I've started filling up from here. That means this tree is not a complete binary tree. What I'll do is I'll take this tree and I'll represent it. I'll represent it in an array, and you will see that there will be gaps in my array. There will be gaps in my array. See, I'll show you. Here, so let me just restore the tree in its original order. Let me just erase these points. Now see, so the root node definitely, which is A, will go at the first index. Its left child, which is B, will go at index, as you can see, 2 into 0 is 0 plus 1 is 1. So B comes here, and its right child will go at 2 into 0 is 0, 0 plus 2 is 2. So it will come here. Now I want to find the left child index of C. See, the left child index of C I want to find because the left child of C is D and I need to know its position in the array. So what is the index of C? The index of C is 2. So its left child will be at index 2 into 2. So here I is 2 because the index of C is 2. I want to find its left child. So I'll substitute 2 in place of I and I'll get 5. Now see, I'll go here at index 5 and insert D. I want to find the position of its right child, the right child of C. What is the index of C? The index of C is 2. So 2 into 2 is 4. 4 plus 2 is 6. So I'll place E at index 6. Now see, these 2 positions have not been filled up. They have been skipped. This is the disadvantage of representing a binary tree which is not complete. Okay, if you represent a binary tree using an array, then the binary tree does not happen to be a complete binary tree. If you represent a binary tree which is not a complete binary tree, using an array, then there will be gaps in your array, like you see in this case. This is not a complete binary tree, that's why you find gaps. This is a complete binary tree, as you can see. That's why there are no gaps in my array. And remember, in order to understand heap sort, of course, you have to understand what heaps are. Heap, the first thing that you need to keep in mind for heaps is, heap is a complete binary tree. And that was the reason why I showed you this representation. It's important for you to understand what a complete binary tree is and how an array representation of it is more beneficial than a linked list representation. Okay, so now what I'll do is, I'll take up the next prerequisite of heaps. So we'll try to understand what heaps are and what are its types. So let's see, okay? Okay, now please note down the definition of heap. I'll dictate the definition. What you do is you pause the video and copy it down from time to time. Suppose H is a complete binary tree. Suppose H is a complete binary tree. It will be termed a heap tree if it satisfies the following properties. Property number 1, for each node n in H, the value at n is greater than the value at n. The value at n is greater than or equal to the value of each of the children of n, greater than or equal to the value of each of the children of n, full stop. Such a heap tree is called a max heap. And property number 2, for each node n in H, the value at n is lesser than or equal to the value of each of the children of n. Such a heap tree is called a min heap. Such a heap tree is called a min heap. So I hope you have noted down the definition. Now what I'll do is, I'll take up 2 examples, as you can see on the board, and I'll try to explain them in the context of the definition that I just dictated. Now let's try to understand what a max heap is. See, what is a max heap? You follow the definition and you will understand that at every node, you consider every node. Okay, I'll just show you the definition, how the definition is satisfied for every node in my max heap. So this is my node. I start with the root node. Now if you observe, the root node contains the maximum value. So all nodes which are present below the root node are lesser than the root node. Okay, so that's what max heap says, that you take any node n in your heap tree H, and you will find that all nodes below it, that means all its descendants, are lesser than it. In max heap, all its descendants will be lesser than it, and in min heap, all its descendants will be greater than it. So in max heap, we saw that we started with 95. So all descendants means all nodes which are below 95. All of them have a value less than 95. Okay. Now let's check the property for 85. So what are the descendants of 85? The descendants of 85 are these. These are the descendants of 85. So all these descendants that you find, 75, 25, 55, 65, all of them are lesser than 85. So the heap property, the max heap property is followed for 85 as well. Let's check for 45. For 45, I can see the descendants are 35 and 15, which are lesser than 45. That means the max heap property is followed for 45 as well. Now 35 and 15, these are my leaf nodes. By default, the max heap property as well as the min heap property will be followed for all leaf nodes. So the max heap property holds in this case as well as in this case, and it holds here as well as here, because these are leaf nodes as well. Now what about 75? What are the descendants of 75? Look at the descendants of 75, 55 and 65. Both of them are lesser than 75. That means the max heap property is followed for 75 as well. And again, 25 is a leaf node, so the max heap property holds for 25 as well. Now let's do the same thing with min heap. Let's look at the first node. Let's start with the root. So all its descendants, that means all these nodes that you can see, these are all the descendants of the root node, and all of them are lesser than the root node. See, you won't find any value which is greater than 15. Now you check the same thing with 45, all its descendants, that means these nodes. These nodes are all greater than 45. See, It's a min heap, right? That means all nodes, all descendants of any node will be lesser than that node. In fact, all descendants of a particular node will be greater than the node, right? Because it's a min heap. So the node is 45. So all nodes which are below it, all its descendants are greater than it. And here, all the descendants were lesser than them. So here I considered 85, all its descendants were lesser than 85. Here, all its descendants will be greater than 45. See, all its descendants are greater. Similarly, 25, all its descendants, 35 and 75, they are greater than 25. For leaf nodes, the heap property, the max heap or the min heap property will hold by default. And what about 55? So look at all the descendants, 85 and 95, both are greater than 55. Okay. So remember, in min heap, all descendants of a particular node will be greater than the node, and in max heap, all descendants will be lesser than a particular node. So if you consider any node, I know I'm being a bit repetitive here, but I just want to make things absolutely clear that in a max heap, if you take any node, all nodes below it, that means all its descendants will be lesser than it. And in a min heap, if you take any node, then all its descendants, if it has any descendants, if it's a leaf node, then the min heap property will hold by default. But if it has any descendants, then all the descendants will be greater than the particular node you're considering. So if I consider 55, all the descendants of 55 will be greater than it. If I consider 45, all its descendants will be greater than it. If I consider 15, the root node will always contain the smallest element of the tree in a min heap. And in a max heap, the root node will always contain the largest element of the tree. So if the largest element is present at the root, then that means all descendants will be lesser. And if the smallest element is present at the root, all descendants will be greater. Okay, so I hope this part is clear. Now what I'll do is, I'll show you how to insert nodes in a heap. Okay, now we have this max heap like we saw, and in this max heap I want to insert 19. I want to insert the node 19. So in order to insert a new node in a heap, what you would do is, first you would insert the node in such a way that it follows the property of complete binary tree. That is step number 1. So let's do that. So I'll insert 19 such that the property of complete binary tree is followed. So where would 19 go? 19 would go to the left of 25. Okay, I'll just change this diagram a bit because I don't have space. Okay, I'll just draw this in a wider manner. So I have 55 here and I have 65 here. Yeah. So this is what my tree is. Now I'll insert 19 such that the property of complete binary tree is followed. That means, of course, the levels that you see, this is the last level, the levels preceding the last level, this one, and this one, level 0, level 1 and level 2, all these levels contain maximum number of nodes, and the last level contains nodes filled up from left to right. So I've filled up the leftmost 2 links. Now I should fill up this one. So 19 goes here. That is step number 1. Next, what you do is, you will check whether the max heap property holds after the insertion of the new node. And if it doesn't hold, then you will have to make necessary swaps such that the heap property holds once again. Now here, as you can see, after inserting 19, the max heap property still holds. Just pause the video for a moment and verify it for yourself that after inserting 19, the max heap property still holds. So I hope you have probably understood. Now, let's say I want to insert 111. I want to insert 111 in this tree. So where would 111 go? Again, following the property of complete binary tree, 111 goes here. But after inserting 111 at its right position, such that the complete binary tree property holds, I can see that the heap property has been violated. So what do? I will start checking the newly inserted node with the parent, and I'll keep checking till I either reach the root node or I find a parent which has a value greater than my current node. What is my current node here? My current node is the newly inserted node. So I'll keep on checking and I'll keep on swapping till the time I find the root node, till the time I reach the root node, or till the time I find a parent node which is greater than my current node. So let's see this, how this is done. So I'll check 111 with 25. Is 25 greater than 111? No. Since it's not, I'll swap them. So 111 would come here and 25 comes here. Done. Now again, I'll check 111 with 85. Is 85 greater than 111? No. So I'll swap it. So let me swap it. So 111 comes here and 85 goes here. Now again, I'll check 111 with 95. Is 111 greater than 90? Is 95 greater than 111? No, it's not. So I need to swap it. The parent has to be greater than the child. That's the property of Max-Heap. So 111 comes here and 95 goes here. Now, can I go any step further up? No, because I've reached the node. Because I've reached the root node. Since I've reached the root node, I cannot go any step up. So I'll stop my swapping operation here. And now, if you observe closely, the Max-Heap property holds. So I hope you have understood why the Max-Heap property still holds. Because you take any node, all its predecessors will be lesser than it. So if I take 45, its predecessors are 35 and 15. They are lesser than it. If I take 95, all its predecessors. In fact, predecessor is not the right term. All its ancestors, right? Or in fact, predecessors is the right term. Okay. I'm getting a bit confused between predecessors and ancestors. Predecessors means the nodes which come after a particular node, and ancestor means the nodes which come before a particular node. So all the predecessors of 95 are greater than it, right? So all nodes, okay, if you find predecessor and ancestor to be confusing, what I would say is you just look at the nodes which are below a particular node. So you look at all the nodes which are below 95. All the nodes which are below 95 are lesser than 95. Similarly, all nodes which are below 45 are lesser than 45. Okay, so the heap property holds. The Max-Heap property holds even after inserting 111. Now the question is, what about the time complexity? So what about the time complexity? Now see, when I inserted 19, I did not require any swap operations. Why? Because after inserting 19, by following the complete binary tree property, it was also found that the heap property holds. So no swapping was required. So in such cases, no swapping is required, and this is known as the best case. That means if I insert a new node in my heap, no swaps are required because the heap property still holds. And in such cases, we would require constant time because no swaps are required. So this is the best case. You insert a node and it follows both the complete binary tree property as well as the heap property. Now, what about the worst case? So this is the best. So ranging from order of 1 to what would be the worst case? Worst case would be what we saw in the case of 111. That means we had to keep on swapping till we went up to the root. That means you can have a maximum number of swaps which is equal to the height of the tree. And remember, height of a complete binary tree. Height of a complete binary tree is log n. Height of a complete binary tree is log n. Remember this, okay? So maximum number of swaps that is required in the worst case is when you would insert a new node and that would be swapped till the point you reach the root. So in such case, you would require maximum number of swaps, and that would be same as the height of the tree. So in the worst case, you would require a time of log n. So in order to insert a new node, the best case is order of 1 when a new node does not require any swaps, and the worst case is same as the height of a complete binary tree, because you would require maximum number of swaps starting from the last level till the time you reach the root. Okay, so I hope you have understood how to insert a new node in an existing heap tree. Now what I'll do is I'll take an example where by repeated insertion operations I will be building a heap tree. Okay, let's see this. So we have been asked to build a max heap by repeatedly inserting these nodes in the order that has been given. That means first I'll insert 19, then 55, followed by 44, and so on. So let's see how we can do this, okay? So what I'll do is, I'll build the max heap step by step, but I'll be doing it on a single tree. But for your examination purpose, what I would suggest is, you show every step with a separate diagram, okay? That means when you're inserting 19, you show step number 1 with a diagram. Then you insert 55. That would be shown through another diagram. Then step 3 has another diagram, and so on. Then that way, you will have no chance of losing marks. So let's just start, okay? So the first node that I have is, so step number 1. So step 1 is, insert 19. Okay, so that's trivial. You're trying to insert into an empty max heap. So 19 goes in. Now step 2. So I hope you're drawing the diagrams separately. So step 2 is insert 55. Insert 55. So where would 55 be inserted? 55 would be inserted to the left of 19, so that the property of complete binary tree is followed. See, after inserting 55, it's still a complete binary tree because I'm inserting from left in the last level. I'm inserting my nodes in the last level from the left hand side. Okay. Now step number 3. Now before going to step number 3, one interesting thing that I just missed out was, look at this. The complete binary tree property is followed. But what about the heap property? 55, I have to check the heap property as well. I missed that out. I'm sorry about that. But I have to check the max heap property after every insertion. So after inserting 55, I can see that 55 is greater than 19. That means I need to swap it. So I need to swap 55 and 19. So 55 comes here and 19 goes here. So you need to check the heap property, max heap property in this case, because I'm trying to build a max heap at every step. Now step number 3 is insert 44. So I want to insert 44. So where would 44 go? 44 would go to the right. So I filled up the last level. Now see, the heap property is still satisfied because the parent of 44, which is 55, is greater than it. So 55 is greater than 44 and 55 is the parent of 44. So the max heap property holds. Now step number 4. Step number 4 is insert 98. So I want to insert 98. So where would 98 go? 98 would go at the last level. Okay, so that makes this tree follow the complete binary tree property. But now I have to check whether the heap property is followed or not, the max heap property. I'll check whether 98 is lesser than its parent or not. But no, 98 happens to be greater than its parent, so I need to swap it. So let me swap it. So 98 would go here and 19 would come here. Next again I'll check 98. So till what time would I keep on checking? Till the time I find a parent which is greater than my current node, or I have reached the root node. So now I'm here 98. 98 I'll check with 55. So if I check 98 and 55, I find that 98 is greater than 55. So I'll swap it. So 98 would come here and 55 would go here. Now after this, the heap property holds. So I don't need to swap any further. Okay. Now you might be wondering that how do you accomplish this in a program? So it's very simple. See, how do you find the parent? Now, if I have to find the parent, what would I do? I would check if, which is my current node. My current node is at index I. So I'm representing it through an array. So let's say if ARR of I is, when will I swap? If ARR of I happens to be greater than the parent. So how do I find the parent index? I find the parent index like this. ARR of, so what would be the parent? If you remember, the parent is I by 2 provided I is odd. If you remember from the initial part of my video, right at the beginning I had mentioned, and it is I by 2, sorry about that, and it is I by 2 minus 1 if it is even. So what will I do? I'll check with its parent. And how do I find the index of the parent? Through the ceil value, through the floor value. So I can somewhere before I can find the parent index. So I can say index parent. So how do I do this? I check if the value of I, that means the current node which I'm talking about, if that is odd, so if I mod 2 is not equal to 0, if it's not equal to 0, then my index parent would be I by 2, and I would take its floor value. So let's say you have a floor function available in your programming language. It's available in C, so I can use this. So I would say floor of I by 2. Otherwise, how would I calculate my index parent? I would calculate my index parent as floor of I by 2 minus 1, because when it's even, I have to subtract 1 from the floor value. And now I'll check whether my current index value, my current node, if it is greater than the node which is present at the parent index. So if it is greater than the index parent, if it happens to be greater than the index parent, then what will I do? Then I'll simply swap. ARR of I and ARR of index parent. So I'll swap them. So what I'll do is, let me just concept. So I hope you have understood this. So what I'll do is I'll take up the entire program. Okay, I'll build the program step by step. But let's just first carry out the tree. Let's just first build the tree. So I hope you have understood this part. Okay, this is pretty clear. You first calculate the index value of the parent. Now the index value of the parent may either be floor of I by 2 or floor of I by 2 minus 1, depending on the value of the index of your current node. The value of the index of your current node will decide the index of the parent. So if it happens to be odd, then it will be a direct floor value, and if it happens to be even, then it will be 1 minus the floor value. And then what will you do? You will check. So this will be inside a loop, right? This entire thing will be inside a loop that you will check every time whether your current value is greater than your parent value. If it happens to be greater, then you will swap. And till what point will you continue this? Till the time you reach the last node. That means till the time you reach the root, or till the time you find a parent node which happens to be greater than your current node. Okay. Now I'll leave the code there. I'll move on. Or what I can do is I can just, due to shortage of space, I think I should erase this part. You can just copy it down. Okay. I'll just erase this part. Okay. Now my next node to insert is, after 98, is 67. So that's step number 5. So step number 5 is insert 67. So I want to insert 67. Now where does 67 go? 67 goes here, according to the property of complete binary tree. But I'm not done. I'll check with the parent of 67. The parent of 67. How do I find the parent of 67? What would be the index of 67? This is 0, 1, 2, 3, 4. So how do I find the parent? I do floor of 4 by 2. So that would be 2. And you check, this is 0, this is 1, this is 2. Now since it's even, so I'll have to subtract 1, like you saw. Had it been odd, then I did not need to subtract this minus 1. But since it's even, since 4 is an even number, I have to subtract 1. So 2 minus 1 is 1. Now look at the element present at index 1. This is at index 0. This is at index 1. So 55 is rightly the parent of 67. Now I find that my current node, which is 67, is greater than its parent. How do I find it? I found it through this formula. Now I'll check whether it's greater. No, the parent is not greater than the current node, so I need to swap it. So I'll swap 67 and 55. So 55 comes here and 67 goes here. Now next I'll check again with the parent of 67. Now the parent of 67, which is 98, happens to be greater than my current node 67. So I don't need to swap. Now you see at this point the Max-Heap property holds. Now I'll go to step number 6. Now at step number 6 I have 48. So let's try to insert 48. Where would 48 go? It would go to the left of 44. But again, I'll have to check with the parent. So parent, which is 44, is lesser than 48. So I need to swap. So here I'll get 48 and here I'll get 44. Again, I'll check with the parent, but the parent is greater than the current node 48. So I don't need to swap it. Next is step number 7. I have to insert 95. I have to insert 95. Where would 95 go? 95 would go to the right of 48, following the property of complete binary tree. I'll check 95 with 48. I'll check 95 with 48. See, 95 happens to be greater than 48, so I need to swap it. So 95 comes here and 48 goes here and 48 goes here. Now what I'll do, I'll check 95 and 98, but 95 is lesser than 98, so I don't need to swap. Next is 66. So I need to insert 66. Now where do I insert 66? I insert 66 here. Now I'll check with the parent. So what is the parent? The parent is 19. It is lesser than 66, so I need to swap it. So 66 comes here and 19 goes here. Now look at the parent of 66. The parent of 66 is 67, which is greater than 66, so I don't need to swap. Now at this point, the Max-Heap property holds, right? See, 98, all nodes below it are lesser than it. 67, all nodes below it are lesser than it. 95, all nodes below it are lesser than it. 55 is a leaf node. 19 is a leaf node. 44 is a leaf node. 48 is a leaf node. For leaf nodes, the Max-Heap property holds by default. Now after 66, I have 70. So let's try to insert 70. So where would 70 go? 70 would go according to the property of complete binary tree at this point. Now I would check. I would check with the parent. So 77 is greater than 66. So I need to swap it. So 70 goes here. 66 comes down here. I've swapped it. Now I'll check with the parent. The parent 67 is lesser than 70. So I need to swap it. So 70 goes here. 67 comes here. Now what I do is, now I check with the parent. The parent is 98, but 98 is greater than 70. So I don't need to swap it any further. Now at this point, the Max-Heap property holds because 70 is greatest among all these nodes. Similarly, 95 is greatest among all these nodes. And in this entire tree, you find the maximum element at the root. That makes it a Max-Heap. So step number 9 is where you have to insert 69. Now let's try to insert 69. Where would 69 go? 69 would go to the left of 55. Now 69 happens to be greater than 55, so I need to swap it. So 69 comes here rather. Yeah, so after swapping, 69 comes here and 55 goes down here. And next I again check with the root, but the root, which is 70, I mean root in the sense, root is not the right term to use. I would say parent. Parent of 69 is 70. 70 is greater than 69, so I don't need to swap. Last element that I need to insert is 30. So there are 10 elements, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think the step numbers, somehow I missed something. So you kindly make the correction. This is step number 11, where I have to insert 30. Now where would 30 go? 30 would go to the right of 69. Now since 69 is greater than 30, I don't need to swap. So I'll stop here. Now this is how you would build a heap, by repeated insertion of the nodes. Now what I would do is I would take this question further and show you how heap sort works. Okay, so I'll just erase this. Now in order to implement heap sort, the first thing that you need to do is you need to build the heap. You need to build the heap by repeated insertions. Like you saw, through repeated insertions, I have built a heap. Now building a heap is same as storing these elements in an array. That means I have an array. Why do I store it in an array? Why do I store a heap in an array? If you remember from the initial part of my video, I had mentioned that complete binary tree would not waste any array memory location. As a result, whenever you want to store a complete binary tree in memory, and a heap happens to be a complete binary tree, whenever you want to store a complete binary tree in your memory, array is the right option, because not only it's simple to implement, but also there is no wastage of space. So here what I would do is I would build this heap. Now building this heap in this way is same as storing it in an array. So how do I store it in an array? I store it in an array by level-wise traversal. So if you remember, how would you implement it programmatically? You would implement it programmatically by applying the formula of left child and right child. And here, how do I do it? Since it's understood to you, like I showed you, that the left child and the right child, the formulas that we used, that is same as the level order insertions. So I would directly insert these nodes using level order traversal. So 98 followed by 70 and 95. See, 98, first you would insert the left child of 98, which is 70, and then you would insert the right child of 98, which is 95. Then you would insert 67 followed by 69. You can apply the formulas and verify, okay? Then you would go for 44 and then 48. Then you would have 19 and then you would have 66. And finally you would have 55 and 30. This is your array, okay? So this is your array of 11 elements. This is your array of 11 elements. Now what do you do? Now, in order to carry out heap sort, you will have to keep on deleting the root. Keep on deleting the root node. And as and when you delete the root node, what happens is you make your readjustments and you will see we'll slowly get a sorted order on this array. So let's see how. And remember, in a heap deletion, when you talk about deletion in case of heaps, you would talk about deleting the root node alone. You are not going to delete any intermediate node. Only deleting the root node has major applications, one of which happens to be heap sort. Now I'm talking about heap sort. So what I'll do is I'll repeatedly delete the root node and make the necessary adjustments. So how do I delete the root node? I would take the root node. What is the root node here? 98. So I would take the root node and I would replace it by the last node in this heap. What is the last node in this heap? The last node in this heap is same as the last node in the array. The last node in the array is 30. So I'll replace 98 by 30. So I would replace 98 by 30, and now this 30, so I would do it two ways, okay? I would do it in the array as well as I would do it here graphically. So here 30 is gone because it has now replaced 98. Okay, that means this 30 is no longer there. This 30 is no longer there. Now what I would do is I would make the necessary adjustments so that this tree maintains its Max-Heap property. How do I do that? Now remember, my heap has now been reduced to 10 elements. Now what I do? I would take my current element, which is 30, and I would check its two children. So I would check 70 and 95. I would find which of the two children is greater. So which is greater out of 70 and 95? 95 is greater. Now, after finding the greater of the two children, I would check that node with my current node. So I would check 95 and 30. Which is 95, which is a child of 30. Is it greater than 30? Yes, it is. If it is greater, then I'll swap it with 30. So 95 comes here and 30 goes here. Done. Now my current node, which is 30, is at this point. Now again, I'll check. What are its two children? 44 and 48. Now out of these two, which is greater? 48 is greater. Now I'll check whether this 48 happens to be greater than 30. Yes, 48 is greater than 30. So I'll swap them. So 48 comes here and 30 goes here. Now see, I have reached a dead end. I have reached a leaf node. That means no more swapping is required. Now you can see, if you closely observe, the Max-Heap property holds on this tree. And now since the heap, I have removed one element, so the size of the heap has reduced from 11 to 10. Now this one unused location, I can use it to insert the node which I just deleted. Which was the node that I just deleted? If you remember, I have just deleted 98. So what I'll do is, I'll simply place or store 98 in this unused location. Okay, fine. Next node to delete is 95. Why? Because 95 is the root. So how do I delete it? I would replace 95 by the last node in the heap. Which is the last node in the heap? 55 is the last node. So I would replace 95. So my current node is, which has been deleted, is 95. I'll place it here, okay? and I'll refer it with X. So my current node which has been deleted is 95 and I'll refer it by X. So what do? I replace 95 with the last node. What is the last node? The last node is 55. Okay. Now before I move into this part. So 95 was here, right? Now the tree, the array has changed, right? The array has changed. So let me make the necessary readjustments. So the array has changed because of the swap operations. The array has changed. As a result, now I have 95 here, then I have 70, then I have 48, then I have 67, 69, 44, 30, 19, 66 and 55. Okay. Now I am in a position to delete 95. So if I delete 95, I would replace it with the last element in my heap. What is the last element in my heap? 55. So 95 would be replaced by 55. That means this 55 no longer exists. It comes up here. It comes up here. So 55 comes here. Now this place is vacant and my heap size has reduced from 10 to 9. So heap size is now reduced from 10 to 9. So these two locations are unused. Okay. Now what I do is, again, I'll do the same operation which I did with when I deleted 98. So here I'll see 55 and I'll compare its children. What are its children? 70 and 48. So out of these two, which is greater? 70 is greater. Since 70 is greater, I'll check whether 70 is greater than 55 or not. Yes, 70 is greater than 55. So I'll swap 70 and 55. So let me swap it here in the array as well, so that I don't need to rewrite it like I had to shortly. So here I swap it. So here I get 55 and here I get 70. Now what do? I'll check. Now my current node is 55. I check its two children. Now out of 67 and 69, which is greater? 69 is greater. Now I compare 69 with 55. Is 69 greater than 55? Yes. So I need to swap it. So I'll swap 55 and 69. So 69 comes here and 55 goes here. And here you have 55 and here you have 69. And here you have 69. Now my current node is 55 and it has reached a dead end, so I don't need to swap any further. So what I do is, I have successfully managed to maintain the heap property even after deletion of 95. But I find this space to be unused. So what I do is, I take my deleted node and I place it there. I place it at this point. Remember, these two elements are no longer part of my heap. Okay. Now next node to delete is 70. So how do I delete 70? So I would now want to delete 70. So my X is 70. So I would replace 70 by the last node. What is the last node? 66. So I would replace 70 by the last node. That means the last element in my array, which is 66. So 66 is no longer present. So 66 is no longer present. Now after this, what do? Now my heap size has reduced. My heap size is once again reduced from 9 to 8. Okay. Now I'll again check. So what are the children of 66, 69 and 48? Why am I doing this? So that the heap property is maintained. So I'll check 69 and 48. How do I find the right child and left child? I'll simply apply the formula. So if you think about it programmatically, I'll simply take up the element at this index, 2 into I plus 1 index, and I'll take up the element at 2 into I plus 2 index, and I'll compare them. Out of the two elements, whichever is greater, like in this case 69 is greater, I'll compare it with the current node, which is 66. So now since 69 is greater than 66, I'll swap it. So I'll swap 66 and 69. So 69 comes here, 66 goes here. So 69 comes here and 66 goes here. Again, I'll compare 66 with its children. Now before comparing, I'll compare the children themselves. So I'll compare 67 and 55, which is greater? 67 is greater. Now I'll check whether 67 is greater than 66. Yes, 67 is greater than 66, so I'll swap them. So here you will get 67 and here you will get 66. So 67 comes here and 66 comes here. Now after this, what do? I'll again check whether I have any children of 66? Yes, I have one child, 19. Is 19 greater than 66? No. So I don't need to swap. So now my heap property holds. Now see, which element did I delete? 70. There is an unused location. Let me place it here. Okay. Now the next element to delete is 69. So first thing that I would do is I would replace 69 with the last element of my array. So I would replace it with 19, and 19 would no longer be present. So 19 is no longer present, and my heap size has further reduced from, so my heap size has reduced to how many elements? 1, 2, 3, 4, 5, 6, 7. It has reduced to 7, and my current value of x. So what have I done? I've replaced it, right? So my current value, my current node, which I have just deleted, is 69, and in place of it, 19 is here. Now I'll check. I'll check the children of 19, 67 and 48. Which is greater? 67 is greater. Now I'll check whether 67 is greater than 19. Yes. So I'll swap it. So I'll swap 67 and 19. So 67 comes here and 19 goes here. So 67 comes here and 19 goes here. And 19 goes here. Now, next I'll check the two children of 19. So they are 66 and 55. Which is greater? 66 is greater. So what will I do? I'll swap. Why will I swap? Because 66 is also greater than 19. So 66 comes here and 19 goes here. That means I have to swap 66 and 19. So 66 comes here and 19 goes here. Now see, 19 is a leaf node, so I don't need to swap any further. Now this place is unused, so I can take my last deleted element 69 and place it here. Now the next element to delete is 67. So I want to delete 67. My heap size has now shrinked to how many elements? 1, 2, 3. So I have deleted, so I currently have how many elements? I have 1, 2, 3, 4, 5, 6, 7. I have 7 elements currently in my heap. I want to delete 67. In fact, have I deleted 67? No, I want to delete 67. So I want to delete 67. It will be replaced by the last node. So the last node is 30. So this place now becomes vacant and 30 is removed. So now I would again check. So 30 comes here at the root. I've swapped it, right? I've swapped it. I've placed it in the first position. I'll check. Its children are 66 and 48. Which is greater? 66 is greater. Now I'll check whether 66 is greater than 30. Yes, it is. So I'll swap it. So I'll swap 66 and 30. The same thing would be done here. 66 and 30 are swapped. So 66 comes here and 30 goes here. Now I'll check 30 with its two children. Now it's out of the two children, 55 is greater and 55 is also greater than 30. So I'll swap 30 and 55. So 55 comes here and 30 goes here. So 55 and 30 are swapped. 55 comes here and 30 goes here. Now after this, I find 30 to be at the leaf node, so no more swappings are required. Now there is an unused location here since my heap has reduced. So there is an unused location. I can place my recently deleted element here. Now the next node to delete is 66. So how would I delete it? I would replace it by the last node. The last node is the last element in the array, which is 44. So I replace it by 44 and I remove 44 from my tree. So 44 is gone. My heap size has further reduced. And now what I do is, so here there is no 66. It has been replaced by 44. Now I check. The two children are 55 and 48. Which is greater? 55 is greater. So I check 55 with 44. Is 55 greater than 44? Yes. So I swap it. So 55 comes here and 44 goes here. So I'll swap 44 and 55. So 55 comes here and 44 goes here. Now what do I do? Now I check again the two children. So out of these two, which is greater? 30 is greater. Now I check whether 30 is greater than 44. But no, 30 is not greater than 44. So I don't need to swap. I'll leave it here. Now I find there is an unused location. The recently deleted element was 66. Yes, the recently deleted element was 66. So let me place it in this unused location. Now the next element to delete is 55. Which is the last element? 30. The last element in the array is 30. So I'll replace 55 with the last element of my array, which is 30. So 30 no longer exists. So this place becomes unused and my heap further shrinks in size. Now again, here I don't have 55 anymore, I have 30. Now I'll check. The two children of 30 are 44 and 48. Which is greater? 48 is greater. So I'll check 48 with 30. Is 48 greater than 30? Yes. So I'll swap it. So 48 comes here and 30 goes here. Now 30 is a leaf node. So let me just swap this. So 48 would come here and 30 goes here. Now since 30 is a leaf node, no more comparisons are required. Now which was the node that I just deleted? I just deleted 55. Okay, I just deleted 55. So let me place 55 here. Now which node do I want to delete? I want to delete 48. Now I want to delete 48. So I'll replace 48 with the last node. Which is the last node? 19. So 48 will be replaced by 19. So 48 is replaced by 19 and 19 is completely removed. So here you can see that the heap has further reduced in size. So this is my heap, right? Now this is my heap. Now I'll check. The children of 19 are 44 and 30. Which is greater? 44 is greater. Now I check 44 with 19. Is 44 greater than 19? Yes. So let me swap it. So 44 comes here and 19 goes here. So here would come 19 and here would come 44. This enables the heap property to be satisfied. Now I have an unused location, so I can place 48 here. The recently deleted node 48 can be placed here. Now I want to delete 44. So the current node that I just deleted was 44. How would I delete it? I would replace 44 with the last node. The last node in my heap is 30. So 44 would be replaced by 30 and 30 no longer exists. So I would remove 30 and here the heap has further shrunk in size. Now I have only two elements, but 30 happens to be greater than 19. So no swaps are required. Now there is an unused location. I can place 44 here. Now what can I do? I can check 30 and 19. So what do I want to delete? I want to delete 30. So here in place of x, I should write 30. So 30 should be replaced by the last node. The last node in the heap is 19. So 19 goes. So 30 is now replaced by 19 and 19 is removed and the heap further shrinks in size to be made up of only one element. Now this unused location, and there is only one element, there is nothing to compare. So I'll take 30, my recently deleted node, my recently deleted root node, and place it in this unused location. Now I have 19, I'll simply delete 19, and this is a trivial case, no swaps are required, and this is my sorted array. So this is how you would apply heap sort on an array of elements. Okay, so this was a fairly long video, and before I conclude, I want to discuss one last thing, that is, what about the time complexity? Okay, what about the time complexity of this? So in order to carry out heap sort, what was the first step? The first step was to build the heap by repeated insertions, like you saw. So by repeated insertions, I was able to build a heap. Now that required how much time? That required, see, in the worst case, how much time would you require to insert a node? If you remember the 111 which I had inserted, I had told you that the worst case time would be same as the height of a complete binary tree. And the height of a complete binary tree is order of log n. So how many nodes do I have to insert? N nodes. And in the worst case, for n nodes, I have to keep on swapping up to the height. So how much time would I require? In order to insert a node, in the worst case, I would require a time of log n. In order to insert one node in the worst case, what would happen in the worst case? You would start from the leaf and you would go up to the root. So you would cover the entire height of the tree. So in order to insert one node in the worst case, you would have to traverse the height. Now in order to insert n nodes, how much time would you require? You would require n into log n time. So this is for building the heap. This is for building the heap. This is the time you need. And now, what do? You keep on deleting, right? you keep on deleting the root. Now, in order to delete a root node, let's say you want to delete only the root node once. You want to delete only the current root node, only one root node. So if you want to delete only one root node, what is the worst possible scenario? You would have to delete that node and you would have to keep checking till the time you reach a leaf node. And in the worst case, you would again have to travel till the height. So like you saw, we were deleting. So let's say the heap was something like this, and you are deleting, you are going here, and then again you are going here. So you are in effect traversing the height. You are traversing the entire height of the tree in order to delete one node in the worst possible case. Now if you do the same thing for n nodes, and what is the height? The height is log n. So in order to delete a node, in order to delete a root node, in the worst case you require height time. You would require time which is same as the height of the tree, and the height of a complete binary tree is log n. So you would require log n time to delete one root, and in order to delete n such roots, you would require n into log n time. So the total time taken is the build heap plus, so you would consider both, right? The build heap time plus the time taken to delete root nodes, and so the total time would be n log n plus n log n, which in effect would give you an overall complexity of order of n log n. So this is the time complexity of heap sort. So I hope this helps. This is probably the longest video I've ever recorded. If you have any doubts, if I've made any slip-ups, please do comment in the section below. Your feedback is what keeps me going. Thank you so very much.